So let me go to the last talk of the workshop. Dr. Daniele Dragoni from Leonardo company. His talk is about quantum computing and Leonardo Labs. Please.
Hello, good evening, everyone. So let me start saying thank you to the organizer for inviting me, and thank you for staying this late. So it's been a long day. I tried to tell you what we are doing at Leonardo in the field of quantum computing. Right, so, sorry. So by now we all understood that quantum computing is a potentially disruptive technology, it promises to solve problems which are computationally hard, and that are even, say, hard to solve on the most powerful supercomputers available today and the supercomputers that will be available in the future. So at the same time, we have understood that quantum computing is the technology has not achieved full maturity yet, and but it's fair to say that essentially the rate of improvements of the technology is very high, and this has led the community to think of the fact that probably useful quantum computers will be available in the future. So it is a matter of when, probably, and not if this will happen. So within this scenario, Leonardo decided to invest in this field and start in 2021 a new quantum computing lab, which is located in Geneva, whose mission is indeed to explore challenges and opportunities associated to this technology, and to build in-house expertise that will be useful to generate a pre-competitive advantage and will be useful to exploit timely and effectively useful quantum computers when they will be available. Okay. And the vision here is to be prepared to have that expertise to deliver tailored solutions to our internal business units, so the Leonardo divisions, plus key selected external clients. Right, so let me stress the fact that our approach here to quantum computing is wants to be quite pragmatic, in the sense that we all know that many platforms exist that can implement the qubits, so might be ion traps, superconductive loops, photons, etc. They all are going through rapid advancements, but they all have pros and cons. So for these reasons, strategically, we decided not really to get into the business of building our own infrastructures, our own platforms, but we are more focusing on benchmarking at the moment the platforms that are available by different vendors while avoiding technology lock-in. And the real focus for us is on algorithms, so developing and testing quantum algorithms, and the applications that could benefit from them. Developing at the same time also advanced in-house capabilities for emulation on RHPC system. Now, concerning quantum algorithms, we have two active research streams. The first one is related to what we call fully quantum algorithms. Here, these algorithms are devised to run on quantum computers, either real devices or emulated devices. And the activity carried out here is done through the development of lighthouse projects with divisions and external clients on use cases that they bring to us at small scale. So here we see high reward, high potential return, but of course this will be in the long term, so more than 5 years. So to mitigate these, let's say, industrial research at very low TRL technologies, so we decided to invest also and explore also quantum-inspired approaches and algorithms, which are not devised to run on quantum computer. These run on classical devices, might be CPU, GPUs, or specialized hardware such as FPGA or other kind of devices. And the idea here for us is to scale up those lighthouse projects developed in the first stream and try to see whether it is possible today or in the near midterm to impact our chain values, so to impact our products. Okay, so here we expect medium sort of return in less than 5 years. Now, this is the infrastructure that we are using to develop our activities. Concerning the emulation part, we are using the Leonardo proprietary HPC system called DaVinci-1. Here you have some specifications. We have more than 60 CPU nodes and more than 80 GPU nodes. By the way, we are also upgrading this system with the latest GPU available on the market. And on this system, we have installed during these years different libraries. Some are reported here, which helped us to emulate up to 36 qubits exactly and up to 1,000 qubits approximately with our approximated approaches. Concerning the quantum resources, as already said, we do not have a quantum hardware, quantum device at the moment installed on-prem. So the idea here is to focus on cloud-based services, but the activity that we are doing in benchmarking these cloud-based devices will be used for scouting solutions, for on-prem solutions for us or for our clients, provided that this yield a clear return on the national ecosystem. Okay. So now these are the application clusters we are working, we are interested in. First of all, combinatorial optimization problems. So here, I mean applications in the field of logistics and telecommunication, air traffic monitoring and control, problems that are relevant here, mission planning, routing, scheduling. We have been quite active in this field. We could publish some papers and some more are coming. Then quantum machine learning. So we are trying to understand how to combine quantum computers and machine learning to make new models, hybrid models with enhanced performances with respect to their classical counterparts. And here, the applications that we envision are in computer vision, NLP, natural language processing, for tasks such as detection, classification, feature extraction, or generative tasks in general. We are engineering companies, so for us it's very important doing physical simulations, so simulations of physical systems. And here I mean computational fluid dynamics, so fluids, electromagnetic waves, propagation, molecules, quantum chemistry, quantum materials, so solving, let's say, Navier-Stokes, Maxwell, and Schrödinger equations with quantum computer. Last but not least, we have a cryptography field, cluster, sorry, where we are trying to monitor the development of the capabilities of quantum computers in breaking encryption protocols such as the RSA key. Okay, so the question is, how far are we from breaking classical encryption protocols? Now, these are very precisely the application classes that we are working on. We have been able to devise to develop let's say, use cases, a variety of use cases, and we'll briefly comment and discuss a couple of them. So the first one that I want to present is the combinatorial optimization problem that we call here antenna problem. So the problem here is the placement of antennas in the aftermath of a natural disaster. So imagine you have a territory hit by a natural disaster, by an earthquake, and you have rescuers moving on the ground to support and assist the population. And the point is that these rescuers have to talk and to communicate with the command post, right? So the point is here is that the wireless communication network has collapsed because there has been an earthquake, and so we need to create a new wireless communication network relying on antennas, okay, which can be dynamically and temporarily deployed on the territory. Each antenna has a signal coverage which is a circular area, and essentially here the problem that we have is to decide where to put these antennas, provided that you have a high number of candidate sites and that you have a limited number of antennas. So placing antennas in order to maximize the signal coverage while minimizing the overlapping regions of neighboring antennas, which means minimizing interference effects. Okay. So this is a sort of simple problem that you can think at, but is computationally very hard. So it is an NP hard problem. Okay. And so we decided to investigate, to tackle this problem with a couple of quantum algorithms, the QA-OA and the QA algorithm. And so we understood very, very interesting things. Okay, and this has been published in this publication. At the same time, we decided to share this sort of problem with our colleagues, so with the academic partners, namely the University of Padua and the University of Bologna, to see and say tackle the same problem with different approaches. And here, the University of Padua somehow is helping us in trying to scale up to solve larger problems using this quantum-inspired approach, which is a tensor network approach, along with variational ground state search, while the University of Bologna is trying to embed this problem onto a real quantum hardware, which is an analog quantum hardware based on neutral atoms. So this is a very difficult task, and it is an ongoing work. At the same time, in the attempt to solve problems at a scale which is relevant for an industry like us, so we decided to create and decided to generate a new library called SPLIT, which stands for Subproblem Parallel Iterative Technique, which is a general purpose quantum-inspired, let's say, let me call it heuristics, quantum-inspired framework to decompose large-scale Kubo problems into smaller subproblems. So imagine you have the Kubo problem and then the dual graph in the top right of the slide, and then you decide to cut this graph into smaller subgraphs, and these subgraphs correspond to smaller subproblems. These are solved in parallel, independently in the first place, and then you, let's say, account for cross interactions between these subproblems, and through an iterative procedure, you're able to couple them, to combine them to yield a global solution, which is maybe not optimal, but close to optimal. And with this approach, with this library, essentially we are able to accommodate natively various hard constraints, and we have been able to solve problems with more than 10,000 binary variables. So this is very interesting also because this library at the moment is just a Python implementation, so there's room for improvements. Second and the last problem, so use case, is the physical simulation, so computational fluid dynamics. Here, so again, we are an engineering company, so we are really interested in computational fluid dynamics because we work in the aerospace sector. So let's say the goal here was, for us, was using quantum enhanced approaches, quantum, let's say, classical hybrid approaches to tackle this problem and say, mimic, say, the evolution of temporal evolution of a fluid system. And so the methodology that we have been working with is based on this flux. Essentially, we start from Navier-Stokes equations in the continuum. We discretize the Navier-Stokes equations onto a regular lattice to get the corresponding algebraic lattice-Boltzmann equations. Then we linearize these equations, and we get a linear system that we then feed to the famous HHL quantum algorithm. And what we have been able to do, I don't know if you see the pointer, but no, probably not. So is what is represented here at the bottom right of the slide. So this is a very, very well-known benchmarking model, the Kolmogorov flow. Here we are representing the velocity field. So you have an initial condition with the periodic boundary conditions, and then you let the system evolve in time, and you see the appearance of vortices that disappear in time because of the dissipation of the system itself. Okay, so this is a very simple problem. So what we are doing at the moment is trying to understand how to use this approach to tackle problems that are more relevant to an industry like Leonardo. So we are talking about these kind of like bottom right sort of simulations. With this, I'm done, and this is the team. So we are 6 people essentially in the team, which is not bad for an industry, especially in Italy. And that's it. Thank you for your attention.
Thank you very much for your presentation. Thank you. Please, question and comments.
So the HPC
Okay.
goal.
Yeah,
So this is
in
quite.
the high performance computing PNRR project.
So what kind of project are you referring to? Is it the Spock 10? So okay, so the HPC and HPC big data and quantum computing project. Okay, so for us is really to explore, investigate with quantum computing, collaborating with other industries and academics and universities. Essentially, this is the final goal. We are aware that there is a long way to get to a point where quantum computers can be useful to us. We are really aware of that. So the point at the moment is really putting together competencies and go the same way, to understand, as best as we can, this very complicated field and how to tackle problems that are relevant to our industry.
Thank you very much. Thank you.
Okay.
Thank you.